Yeah, so hi everyone, welcome to this new edition of the Cambridge Cheminformatics meeting, both at CCDC in Cambridge and also online. The Zoom meeting will be recorded, and if at any point you have any questions, you can always ask the question on Zoom, and we'll go around with the microphone at CCDC. So today, we have three very interesting talks. So we have Patrick talking about assessing conformation of small molecules in the CSD. We'll have Nicholas talking about 3D generative model and guided diffusion. And we'll have Androit talking about from data mangling to data wrangling. Just a first housekeeping slide for people here at CCDC, some fire safety information. So you have sign in at the table downstairs, so don't forget to sign out when you're leaving the building. Also, there's no fire alarm that should occur. So if you hear the fire alarm, please exit the building through the nearest fire exit. And the point of gathering for the fire exit is in the park, the car park just behind CCDC. So I think that's pretty much it for the information. So we'll start the presentation with the first presenter, who is Patrick McCabe from CCDC. So I will share the presentation online, make sure everything is going smoothly. Okay. Yeah. Can you see the presentation in full screen on Zoom?
Yes, it's working. Thanks.
Okay, perfect. Thank you very much. So yeah, let's go back to the beginning. Okay, yeah, thanks, Patrick. The floor is yours.
Okay, thank you. Thanks, Benoit. Good afternoon, everybody. I'm Patrick. I'm a data analyst here.
Yeah, sorry, just modifying something in the second screen. Okay. Yeah. Yeah, because at CCDC we have the other screen. So yeah.
Always does this to me. It's the wrong one.
Which top left? Oh yeah, on the other one. Yeah, but I think I'm afraid that if I do that on Zoom, they will have the yeah. But I think it's with the Mac. Yeah, because here we have the presenter view. So can you just confirm that online you have the full screen or the presenter view?
It's a presenter view.
Yeah, no, they have the presenter view. Okay.
Swap displays.
Yeah, but because we have two screens, we have the laptop screen and we have the CCDC screen, so we have to set up the.
Can you set the display so it just extends on, so it duplicates on there rather than extending?
I will try to find that.
I know how to do it on Windows, but
displays.
yeah, mirror, that's it.
Yeah, but I think it was already on mirror, so okay, I think it's only what on the PowerPoint thing. So if I click here, okay, maybe I will just try to keep the presenter here. Sorry about that. Okay, yeah, that was better. Sorry about the inconvenience. That was the double setup, which was a bit confusing. Okay, so let's start now. Thank you.
Okay. Seems to work, yeah. So, welcome and thank you for listening to me this afternoon. My talk is about assessing small molecule conformations against the Cambridge Structural Database. So conformations, we all know they're extremely important in the wide umbrella of drug design or crystal structure prediction. But to talk about conformations, we need some sense of what's good, what's bad, what's unusual, what's not unusual. We need to think about concepts to define good and bad. So we've got a rotating heptane molecule here, and I'm suspecting most people are thinking that's kind of a good conformation. So we have some concepts in our minds about what's good and what's bad. To define good and bad in general, there are different ways one can approach that problem. We can use our intuition, our gut feeling, or expert opinion, if you want to express it like that. Lots of experts in the room. Perhaps we want to be a little less subjective and a bit more objective. One could use energetics, for example, high-level theoretical quantum chemistry calculations. We take the lowest energy, we say that's better, assuming entropic effects neglected, or we're working at absolute zero or something like that. And then there's data, the results of experiments. And today we like to talk about big data, or at least by today's standards, though wouldn't it be interesting to know in 100, 200 years' time what kind of volumes of data people are dealing with then. And because we're talking about data right now, I must mention the Cambridge Structural Database. We are in the Cambridge Crystallographic Data Centre, which makes the Cambridge Structural Database. And presently there's over 1.25 million curated crystal structures in that database. So maybe you'd like to describe that as big data. But we start homing in on the topic today's talk, which is about conformations. Well, conformations are all about 3D shapes of molecules and geometries. And in this little study, we've split the shape, broken it down into bond lengths, valence angles, and rotatable bonds to define that geometry and that shape. So working in terms of those internal coordinates. We're not treating rings as separate entities in their own right. We're treating rings as composites of bond lengths, valence angles, and torsion angles. Well, CDC already has a tool for assessing molecular geometry, and some of us heard a great deal about this yesterday from John Liebschutz. This is the MOGL program, which assesses an input molecular conformation against predefined, precompiled libraries of bond lengths and valence angles, torsion angles. So it looks at the bond lengths in your molecule and assesses where that length lies against the pre-computed distributions. Mogul's nearly 20 years old now. Came out in 2004. And the quantitative measures that Mogul uses are Z-scores. Let me try and get a pointer. This is a Mac, sorry, you can't operate the
Set up the laser pointer.
Thank you. Yeah. Z-scores for the bond lengths and the valence angles, and a different score, local density for rotatable bonds. As a reminder, the Z-score assesses your observation X against the mean and standard deviation of your predefined distribution. So how far you are from the mean in units of standard deviations. I think that's well known. I think it's less well known that Z-scores can be misleading in certain circumstances. And the local density requires a somewhat arbitrary definition of what local means. Is local plus or minus 5 degrees? Is it plus or minus 15? Is it plus or minus 30? That choice is arbitrary, and it is kind of up to you. Another thing to point out about these measures is they are what I would describe as heterogeneous measures. It's a different type of score for bond lengths and valence angles compared to the score you use for the torsion angles. And Mogul does not give you a score for your conformation as a whole, as an entity in itself. So I want to spend a minute talking about Z-scores. People really tend to come up with a threshold and say, Z is greater than 2, then I'm going to define that observation as unusual, and conversely, less than 2 or whatever threshold you decide on is taken as being okay. There are issues with dichotomizing continuous variables like this. If you have a score of 2.05, you're saying that's unusual. Things light up as red, and you have to go off and investigate. And if it's 1.95, you get a green light and you forget about it. 1.95 and 2.05 are, to all intents and purposes, just the same. So you may want to play the conservative game and say, well, if it's less than 1, I'm going to be happy with that observation. And then you may just go silly and say, Z is less than 0.5. We're going to be absolutely 100% confident this observation is a good one. There's a counter example. This vertical blue line is an observation with Z equals 0.5, and that does not even lie in the range of previously seen observations. And this is not a lack of data problem. There are 1,000 observations in that history. So an alternative way, perhaps, to think about unusual, not unusual, is to think about the probability density function of your observations. So that's what this curve is here, this solid black line. I've got an observation marked with a dashed dot green line. And instead of comparing it to the mean standard deviation, you take the value of the probability density function at that observation and compare it to the PDF at the highest mode, which is that vertical line x equals 2. This is this Q value, this ratio quotient. So imaginative like that. Q is a number that belongs to the range 0 and 1. And the closer to 1 you get, the better your observation. That's the claim. Z ranges from -infinity to infinity, where the Z score closer to 0 you are, the better. So now we've got this new score Q. How does it compare to Z? So here's a histogram with fitted PDF in red. The mode is here and the mean of this histogram is here. And we've got an observation close to the mean. And the Z score is quite low. Suggests it's a pretty good observation. Q is 0.5, which might suggest it's only a mediocre observation. If, however, we move that observation close to the mode, Z's gone up by about a factor of 5, which means interpreting Z scores, that's a much worse observation than we had before. But now the Q value has gone up to about 0.98, suggesting it's a more likely observation, better observation. And it might be a better observation because it's in a region of more frequently observed values. The reason we don't use Z scores for multimodal distributions, like you typically see with torsion angles, is show that on this slide. So on the left-hand side, we've got an observation in the valley of this bimodal distribution, which is very close to the mean of that distribution. So Z is very close to 0, suggesting that's a fantastic observation. Q close to 0 too. The way you interpret Q, that suggests it's quite an unlikely observation. If we move the observation close to the biggest mode, Z has increased by a factor of 20, suggesting a much worse observation than the one on the left-hand side. Clearly, that's not the case. And Q has gone to about 1, suggesting a highly likely observation, which is the case. Another thing the Q score addresses is this heterogeneity of measures. No longer need different types of score for different parts of your molecule. So you can use the same Q score for your bond lengths, as for your valence angles, as for your torsion angles. And that kind of lends itself to fusing these values together, combining them a bit more readily into an overall score for your actual conformation. I think there are lots of ways you might think of combining these individual Q values together to get a single value for your conformation, like arithmetic mean or geometric mean. If you wanted to be a bit more sophisticated, you could start weighting the different Qs. If you're more interested in torsions, you'd weight those. But we've gone with geometric mean. Geometric mean, 2 numbers, multiply them together and take the square root. Geometric mean of n numbers, you multiply them all together and take the nth root. So what we do, we take the individual Q values for the individual attributes, and we can construct these ensemble scores. So a Q value for the ensemble of bond lengths, or the ensemble of valence angles, ensemble of torsion angles. Yeah. So for the bond lengths, you multiply all the Qs and you raise it to 1 over the number of contributing bond lengths. And you can do that for the conformation as a whole. You multiply all the bond length Qs times all the valence angle Qs and all the rotatable Qs and raise it to the appropriate power. This is a conservative measure. So any one single bad score, any one single bad Q value will lead to a bad conformation score. But you can dream up whatever combinations are fit for your purpose. So that's that's kind of the first half of the talk, which is like the concepts and the background. And now it's about results. How does this look in practice? Now, if you run it across the CSD and look for Q values that could be considered to be very high, like greater than 0.95, well, there's a selection there. So that spinning heptane that we saw early on, that I suspected you may think is a nice confirmation, does score very highly. The table at the bottom shows the overall score for the confirmation, and it shows the ensemble scores as well for the bond lengths and valence angles and the rotatable bonds, and a couple of other examples there too. I think it's more interesting to look at the ones that don't score so highly. So this Abimut has a Q score for its confirmation, which is 0 to 2 decimal places. And the bond length score is 0.02, the valence angle score is 0 to 2 decimal places, and the rotatable bonds are not doing too bad in this structure, but there's something up with bond lengths and the valence angles. So you start drilling down into individual Q scores. So here are all the Q scores for the bond lengths here. You can see how they tail off to some very small values. And if you look at the actual histogram, this is the C carbon oxygen bond length, which happens to be the second one here. This is quite a left skewed histogram, so we can't assume symmetric bond length histograms when we're analyzing these molecules. And that's the actual bond length, and that's the distribution, and that leads to that Q. But if you look at the phosphorus carbon bond length, well, the distribution itself is quite interesting. There's a hint of bimodality. Well, the bond length looks way too long. And this is the P1C4, so it's right down towards the 0 end. And this C8, C7 bond length is actually getting a Q value of 0. It's nowhere near that histogram. At the valence angles, you can look at the same kind of picture. So we have all the valence angles plotted here. And these are all their individual Q scores. And this is C7, C12, C11. It's 3 carbon atoms together. This is the value of that valence angle. Perhaps it doesn't come out so well on that that figure with the axis labeling, but this is 120 degrees. You've got 3 carbon atoms joined together that really want to be 120 degrees. So that happens to be that angle in that phenyl ring, which is 113.8 degrees in that structure, as opposed to 120 degrees, which what you might expect to be in a phenyl ring. So that's one application. Another is related to the very nice conformer generator that CCDC produces. So by design, this conformer generator doesn't adjust bond lengths or valence angles, but it obviously adjusts torsion angles. If you have 250 conformations, how might you verify that all the bond lengths are the same in all those conformations and all the valence angles are the same? Well, probably multiple ways of doing it, but you can leverage these ensemble Q scores. I think if bond lengths aren't varying, then you'd expect the same ensemble Q score across all the conformations generated. So each point here is a generated conformer, and this is the bond length Q score for all of those conformers, and they're all the same. Bond lengths aren't varying. This is the same graph, but for the valence angles. And this is the graph for the torsion angles, so you can see how strongly the Q score is associated with torsion angles, and obviously this confirms the torsions are changing, bond lengths aren't, and valences aren't. Final example showing today are the results for running it against platinum diverse set, high quality data set of protein bound ligand conformations. The plot here shows the Q score for the conformations themselves, and then we have the Q scores for the bond lengths and Q scores for the valence angles and the Q scores for the torsion angles in those ligands. The histogram for the torsion angles does indeed lean towards the right and high scores, so suggesting that when you compare against this data set, these torsions are quite CSD-like, and this data set could be considered high quality. But if you're also interested in valence angles and torsion angles, well then, maybe they're not so high quality when you compare against CSD. And you get these inflated peaks at zero, for reasons we've seen in an earlier example. So in conclusion, we've kind of introduced a newer concept for defining good and bad, well, not relative to the mean, but relative to the mode. And we have a quantitative measure to assess that. The Q value, we like it here because it's a homogeneous approach. Don't need different types of scores for different types of attributes of your molecule, and it works whether your distributions are skewed or not, or multimodal or not, unlike the Zs. And that's the final slide. So thank you for your attention.
Thank you very much, Patrick. Do we have any questions in the audience or online? Well, I have a question then. So when you look at the Q values of the platinum data sets, and we see that the valence angles, there's a lot which have a Q value close to zero. Do you think it's because the distribution of these angles are different between the CSD and the PDB, or do you think it's because of how we have refined the ligand model in the PDB, something got wrong at some point, or we tried to fit it too much in the electron density, or the fitting was wrong? What's your opinion on that?
Well, of course, yeah, the CSD is small molecule data. It's not macromolecule protein data. But it has been shown that small molecule crystallographic database data is relevant to ligands bound in the PDB.
Yeah, it made me think of the webinar we had yesterday from John about the good, the bad, and twisted. So very nice. Any other questions in the audience? Oh, okay. Maybe. Yeah, Ernest, you have a question if you want to unmute yourself.
Thank you. So many times when we have a multimodal distribution, we don't actually know how many modes there are. So yeah, do we have to find out how many modes there are by eye, or because in many distributions it can get very complicated?
Yeah,
thank you.
This picks the largest mode, so that's quite easy to find. So it always compares it to the largest mode.
Okay, and Andreas as well. Torstov, if you have a question, you can unmute yourself. Yeah. We cannot hear you. I think you are unmuted, but we don't hear you speaking. So you can also ask the question in the chat and we can answer. How do you deal with saturated rings?
They're treated like, as I said, as composites of the valence angles and the torsion angles. The libraries contain cyclic and acyclic torsions, and the keys will try to find the most appropriate library for the fragment at hand.
Yeah.
So does this also handle organometallics, things like that?
Well, the data set it excludes metals, if I remember correctly. So this doesn't. But I mean, this is about you know, the principle, I think, of using the mode rather than the mean. So if people have their in-house data sets, they can build them and use this kind of approach to assess their conformations. John? Well, there could be. I think there needs to be conversations to take place in-house about how to productize this. Yeah, but it would be nice to see it in the product. You know, watch this space, I guess.
Okay, one final question. Okay. Yeah, sorry. Can think about it next time.
Thank you.
Yeah, okay. Thanks a lot, everyone, for the questions. And let's thank Patrick again for our presentation. And our next speaker is Nicolas Runcie, who will talk about his wonderful molecule generation model.
Can you also add on the pointer, please?
Sorry?
Can you also add the pointer?
Yeah. Yeah, I need to make the slideshow. Here we go. Okay, I think it's all good. Yeah.
Brilliant. Thank you very much for having me. I'm very excited to be here. My name is Nicholas. I am a medicinal and biological chemistry student from the University of Edinburgh. And the research I'm presenting today, I did during my final year of undergrad. I just did it in my spare time because it was fun and really cool. And I currently work at AstraZeneca as a master's placement student. But I need to make it very clear that all the work I'm presenting I did before I joined AstraZeneca, and all opinions are my own. So to understand this work, we need to understand two key concepts. And first of all, we got fragment-based drug design. This is a design methodology used within drug discovery where you take your protein target and you crystallize it with some small organic molecules. And these small organic molecules don't necessarily have measurable affinity, but if you have enough of these fragments bound within the active site, you can sort of look at the fragments and figure out how to merge them together or link them together. And you can use these to inspire a drug-like molecule. And the data set I used for this was, of course, the COVID moonshot data set. So back in 2020, when COVID hit, these researchers took the SARS-CoV-2 main protease, which is the target you would use to make an antiviral for COVID. And they did a full fragment screen. They published all data online for free for everyone to use. And they asked for submissions from the public of sort of drug ideas. And within 1 week, they had 2,000 submissions. A week later, they had 2,000 more. And they like synthesized, tested, and they did a full drug discovery project, completely open source and public, putting all data online. And within 2 months, they had a preclinical candidate. So it's a truly fantastic data set, lots of drug-like data in there. And what I used from this data set were the 23 non-covalent hits that they had right at the beginning, sort of from day one, the really sparse information that they had. And this was to represent the sparse information that's known at the beginning of a drug discovery project. So that's fragment-based drug design. Next, we need to understand diffusion models. And diffusion models have been exceptionally successful in recent years in AI image generation. Pretty much every image generator I can think of is a diffusion model. For example, on the screen here, I've got an image by Daley 3. I asked it to make an image of a molecule looking at a painting of a molecule. So this is like really meta cheminformatics right here. And the images that are generated by these models are so fantastically impressive. They seem to capture the creativity that humans have, and they obey so many constraints. And I think to myself that what if we can make a diffusion model that sort of captures the essence of chemistry and can be used for drug discovery? So that sort of forms the foundation of this project. And to understand how diffusion models work, I like to introduce how image generation diffusion works, and then I sort of by analogy explain how molecule generation works. So the way that these diffusion models work, let's look at the first at the top, an image of a stick man. The diffusion process involves taking an image and then applying some noise to it, and we get a slightly noisy image. And then we take that image and then apply a bit more noise to it. And we iteratively add noise to the image until we completely destroy the image and we're left with just pure noise at the very end. So that's the diffusion process. The denoising process, which is a machine learning bit, is we train a machine learning model so that for any given time step, we can predict the image that came slightly before. So here we got time step 2, a noisy stick man. What was the image that came slightly before, the slightly less noisy image? And you do this across all time steps for all sorts of images. And then the result is that you can just enter any random distribution of noise at the beginning, apply the full denoising process, and you'll get out images that resemble your training set. And the fact that this works, I still don't believe it, but it does, and it's really effective. So by analogy, we can use the same idea for molecules. This time we take our molecule and we ignore all bonding information. So we just consider the atomic coordinates. And this time for our diffusion process, we take the coordinates and we apply noise to the coordinates themselves. So we slightly jumble up the coordinates, iteratively adding Gaussian noise so that the coordinates slowly get destroyed over a series of time steps until we arrive at just a pure Gaussian distribution of noise coordinates. And again, the machine learning bit is that we learn the reverse process. For any given time step of molecule, what was the molecule that came slightly before? So for time step 1, we've got a noisy set of coordinates. How do we move those coordinates to make it look a bit more like a molecule? So of course, molecules are a bit more complicated than just images. They're 3-dimensional. So this model uses like equivariant neural networks and considers the molecules in 3 dimensions. What equivariant means is that a molecule is the same when you look at it and if you move it in space or rotate it. So the equivariant diffusion model considers this property as part of the generative process just by design. So that's all really cool, and it works. So when I was playing with this, I took a GitHub repo for molecule generation, and I was playing with it. It's really cool, but it's not particularly useful yet for drug discovery because we're wanting to make molecules that are conditioned according to a protein pocket for a given drug target. And there are ways that you can achieve this. You can train a model specifically based on protein information and molecule information and try and make a joint conditional distribution type diffusion model, but that's quite complicated. And also I was doing this in my bedroom using Google Colab. I did not have the resources to retrain a model. So I had to figure out a way to achieve conditional generation without ever having to retrain the model that I used. So all of the work I present here is using a diffusion model that I got off of GitHub, already trained using publicly available weights. And the rest of this work shows how we achieve conditional generation without any more training. So when I looked to the literature, I found this method called iterative latent variable refinement. And what these researchers did was they trained a diffusion model for face generation. And so this was just a random face generator. And what they did is within the generative process, during that denoising process, after they've done all their training, just when they click play and run, they inject some information from a reference face into that generative process. And what they were able to do was guide generation towards generating faces that look a bit like that reference face. So if you look at this guy up here, you can see that all of these faces down here look a bit like the same reference. Additionally, you can see that as we go down the series of faces, they have captured a sort of diversity measure here. So as we go down, the faces diverge away from that reference, and we get new faces that still look like that reference, but are clearly very different. And I saw this and I thought, well, you know what, that's pretty much fragment-based drug design. You've got this fragment data and, you know, it's not quite a drug by itself, but we want to use this data to inspire a drug-like molecule. So what I did is essentially made this work for molecules using equivariant diffusion models in 3 dimensions. And the way it works is, I think, surprisingly simple. So we're looking here at the latent space of the diffusion process, just at a single time step. And the light blue circle that we have up here is a single coordinate being suggested by that diffusion model during the denoising process. And left by itself, that light blue circle is instantiated at the beginning as just noise, and then will float around during like 1,000 steps of denoising until it arrives at a position that looks like a molecule. But that is a random molecule it's generating. What I do is I add in information of a reference. So here that's represented by the light pink circle. So what I do is I take a reference coordinate and I bring that up to the same time step as the denoising process is on. So say we've done this generative denoising process and we're now in time step 30. I bring the reference coordinate up to time step 30. So we're playing in the same latent space. Then what I do is simply I nudge the coordinate suggested by the diffusion model in the direction of that noised reference. So literally just move it in the direction of that reference. It's just a simple nudge. That's what SILVR is referring to this mechanism. And the extent by which you refine and do that nudging is defined by the SILVR rate. So if you set SILVR rate to 0, there's no refinement. You just leave the coordinate as it is. You can set it to 1, and that would be total replacement, moving it all the way down to where the reference is. And a value of SILVR rate between like 0 and 1 modulates how much refinement we're doing. So we have a variable parameter here defining how much conditioning we're wanting to implement. So that's the idea. If I've lost you, now's the time to come back, because this is the model in action. It looks quite nice. So if you look at underlying, we've got wires that represent 2 fragments that are bound within the active site of the main protease. And the spheres that are floating around is the diffusion model generating a molecule. And I'll just remind, because I want to make this so clear, that the diffusion model is an unconditional model. I just got it off of GitHub. And what I've done is I've applied the slight modification when I click play that injects that information of the reference fragments. And I'm able to guide the generation towards making molecules that look like these fragments. So if we look at the process, you can see the spheres start off sort of in the center, like that's the Gaussian distribution of noise. And then as time goes on, they spread out. They start exploring the area described by the fragments. And then eventually they sort of stabilize in a position that looks like the fragments, but also looks like a valid looking molecule. And I say that SILVR rate is a variable parameter, so we can repeat this experiment using different values of SILVR rate. So for using these fragments on the left as the reference to guide the generation, if we have SILVR rate to 0, the molecules that are generated are totally random. They got no alignment in space or anything, just random molecules. Increase the value slightly, and we now get maybe like a slight alignment, but not much going on. If you increase the value a bit further, we can now see that the molecules that are generated are in the same plane as the reference fragments. And you maybe have some indication of ring structures appearing in the correct position. Go a bit further, and we now get molecules that have a somewhat strong resemblance to the reference fragments. And you got rings in similar positions, and you've also got some heteroatoms now being preserved. And then we go up to a high value of SILVR rate, and now we've got absolute preservation of that 6-membered ring. We've got heteroatoms in the same place, and it looks kind of good if you're a computing scientist. If you're a chemist, you look at these molecules and think they're absolutely atrocious. It gets a bit better later on, don't worry. So we can look at the data. We do lots of experiments like lots of samples, we can analyze the behavior of this molecule, of this model. So because of how this model is set up, there's a one-to-one mapping of atoms within the reference fragments and the sampled molecule. And because there's a one-to-one mapping, you can simply calculate the RMSD, which is quite convenient. And you can see that as you increase the SILVR rate, the RMSD decreases, which means that the molecules we're generating are now spatially more similar to those reference fragments. So we've got indication here that the SILVR rate does in fact sort of define how similar the generated molecules will be to those reference fragments. If we go a bit further, we can also consider some benchmarking on whether this model works. The way that at the time all these diffusion models were being tested was with atom stability. So this measure considers whether the valence of each atom within the molecule is satisfied. And if the valence of each atom is satisfied, then that atom is described as stable. And the underlying model that I was using from GitHub had a performance of like 80% of the atoms were stable, which isn't great, but that's what we were working with. And you can see that as you start to apply SILVR conditioning, the performance of the condition model sort of resembles that of the underlying model. I think the evidence that we have here, like it looks like the performance actually falls off, but if you repeat the experiment under slightly different conditions with more atoms and more fragments, and also there's a technical issue that goes on with hydrogen atoms. So in fact, when you look at the molecules that are generated, like actually in person, the performance of the quality of molecules over a variety of SILVR rates resembles that of the underlying model. So that's good. It means that SILVR is not harming the quality of generation. This other benchmarking method I used was geometry stability. So in principle, the generative model should be generating molecules in the ground state conformation. And what I was thinking is that ideally the generated molecule should also be in a ground state conformation. So I took the generated molecule, took a predicted conformation of what that should be, compared it to the generated conformation, looked at the RMSD to see whether they were in agreement. And we can see again that up to a moderate value of SILVR rates, the quality of generated molecules resembles that of the underlying model. So the evidence shows that SILVR doesn't really harm the quality of generated molecules. The most exciting result, though, is from shape complementarity. So this is a measure that describes how similar in shape the protein pocket is to the ligand. It's sort of like a docking score, but without any electrostatics. It's just a shape agreement. And you can see that as we increase SILVR rate, the molecules have a far better shape agreement, which means that these molecules are now complementary to the protein binding site, which is good because that is sort of a necessary condition required for drug discovery. And then finally, I demonstrated this method for fragment-based drug design type tasks. So these are a few examples of just fragments that I tried merging and linking and see what happens. My favorite molecule that we generated was on the top here. So these are 3 separate fragments that are really quite complicated, and I don't think any human could reasonably interpret this type of data. But if you enter that into SILVR and do the whole guidance, you can generate a seemingly reasonable molecule. The rings are in the same positions, and my favorite thing is right here. So on the reference fragments, we have an amide and a sulfonyl fluoride, and that has been turned into a cyclic sulfamate. So it's formed a ring, it's made this new scaffold, and I think that sort of group there is quite a reasonable idea. At least I think it is. I think this whole thing looks quite nice. Well, with a pinch of salt. Go down one line, we've got 2 fragments here. So again, 2 disconnected fragments. Applying the SILVR protocol, they get merged together, generate a new scaffold. And again, I mean, this group looks quite nice to me. I don't think you can actually synthesize that, but again, it's a nice looking molecule. And again, it of course fits within the pocket. And then finally, I showed sort of a fragment linking idea. So I picked 2 fragments that were orthogonal to each other that were really quite complicated. Like it didn't really make sense how you'd want to connect them together. There was no obvious vector. And again, I entered it in and I was able to connect them together using SILVR. So it's quite nice. However, there's lots of issues with this method. So all the evidence that we have is that the silver conditioning is great, but the limiting factor is the quality of the underlying model. So if you have a really powerful diffusion model, you should be able to use silver at runtime to make a sort of a fragment-based drug design type tool. So if you want to go and train up a really powerful diffusion model, I highly recommend. Benchmarking, I'm so glad that Postbusters wasn't out before we did this paper, because this would have failed every single benchmark you can imagine. The quality of molecules are not great, but also I think benchmarking as a whole within generative modeling, there's lots of open questions about like what a good generative model looks like. It's slow. It takes about 1 minute per GPU to generate a molecule. I thought that was slow, but actually, in hindsight, I think given the resources that pharma has, I think that's actually a totally reasonable time to spend generating one molecule, especially if it's particularly good. And the final one, the absolute key one that I'm sure everyone is thinking is like the synthetic feasibility. These are awful molecules. So if we look at the SA score on the right, this quantifies how synthesizable molecules are. Really, you're wanting it around to be 3. 3 is sort of like a reasonable score for SA. A score above 7 is like the most complicated natural product you've ever seen. And I think that the scores that I have here indicate that these molecules are not even possible to make. So that's not great. However, there's some light at the end of the tunnel. So I realized these issues, and over the summer, I worked with the ASAP consortium, which they were founded out the back of COVID Moonshot to develop antivirals for viruses which could become pandemics in the future. It's a really great initiative. Again, it's like open source and a nice project. So I worked with ASAP over the summer with a scholarship, and I developed a new version of SILVR, which performs a lot better. So if we look at the SA score, this time, all the molecules that are generated are within synthesizable range, which is very nice. And if you look at the structures, I think the structures that I'm showing here look a lot more like drugs, or at least better than what was previously shown. So I think there's a light at the end of the tunnel here. And if we go one step further, ideally, the molecules that we generate, you want to be able to make and buy quite easily. So I did a quick enamine query. The query I did wasn't an exact match, but like a very close match within 1 or 2 atoms difference. And I found that 68% of the molecules that I queried from SILVR resulted in a hit within enamine. So there's indication that this new model has got potential. And within ASAP, we briefly tried it on a few targets. I don't know what they're doing right now. I don't hear anything from them anymore, but we did try it on a few different targets, and it was making some quite nice results. So watch this space. I hope that the work's going to continue on this. My proposal for doing a PhD later, the SILVR 2 sort of forms a foundation. So if there's anyone wanting to explore SILVR 2 further, reach out to me. But with that, I'll give you the key take-home messages. So the main thing is that SILVR is a conditioning method for diffusion models for molecule generation. If you have a diffusion model that can make molecules, you can apply SILVR at runtime to achieve conditional generation. The extent of conditioning can be defined by the SILVR rate. That's just a tunable parameter that you can enter. And what's quite nice is that you can get shape complementarity to the binding site just by considering the reference fragments alone. And with that, I'd like to thank a whole number of people. So the COVID Moonshot project, they've got fantastic data set, really grateful for that. ASAP for funding me this summer, that was really nice of them. Matteo and John for reading over my preprint before we submitted it. And Antonia May. Tony is just the most fantastic supervisor ever. This work I did as an undergrad just because I wanted to, and out of nowhere, she was so supportive and really helped me do all of this, which I'm so grateful for. And her whole group is really lovely. So I highly recommend reaching out to her for collaborations and all sorts. And with that, I'll take any questions. Thank you.
Thanks, Nicholas, for the brilliant talk. Is there any question in the audience? And I will also check online if there's questions. Yeah.
This might be a trivial question, but how do you decide how many atoms to put in at the start?
So yes, so by default, we use the number of atoms that are on the fragments. So there's actually a whole series of things that happen here by accident that work quite well. So on the fragments, there's no hydrogen atoms, and the generative model produces hydrogen atoms. So if you have like 3 fragments that are overlaid with that are like carbon rich, lots of heavy atoms there, say you've got 50 atoms, during the generative process, lots of those atoms get mapped to hydrogens just by the nature of how the model works. So it sort of naturally is able to balance itself out and generate molecules. So like there will always be like 50 atoms because that's how many there were on the fragments, but some of them get turned into hydrogen, so it might look like there's less heavy atoms. I did also try this other thing with dummy atoms, so atoms that aren't explicitly guided, and that's how I did the fragment linking. The performance did improve. I think there's scope for improvement for adding in these additional atoms. There's all sorts of small technical details that need to be ironed out before this becomes like a really useful tool. But yeah, I hope that answers.
Thank
you. Hi, with AlphaFold, at the very last step, it will do a cleanup with a force field, amber force field. Have you considered cleaning up your molecule at the last step with something like a small molecule force field or a neural net potential like AIMnet2 or something?
It's a good idea. That's what you presented last time, isn't it? Did you present that idea last time?
Yes, so I presented the benchmarking of generative models.
So I think adding in a step at the end would probably improve the quality of structures generated. I think that's reasonable. Yeah. Yeah.
Yeah, it's pretty much needs to be refined. I mean, your model and there's like much other model which are guided by structures, like pocket structures, and most of the times there are issues like steric clashes, invalid bond length angles. I mean, if you use the Q value that Patrick talked about just before, they would not have a like high value. So yes, there's room for improvement, and structure needs to be refined. And also like the pocket structures, like there's always 1 or 2 things which are wrong, like inferring the residue atoms, etc.
Although what's particularly bad about this model is that because it's only considering the coordinates, you have to infer the molecular graph as a final step. So actually applying any sorts of post-processing was really quite difficult. And that's why all my benchmarking was sort of just based off of crude 3D ideas because the molecular graph was ambiguous itself.
Hi there. Is there any way you could concatenate these models to refine it by AI instead of, to be structurally sensible? And, you're doing part of that connectivity, but is there another way of being synthetically sensible, training it?
For the quality
from the output,
like for post-processing? Or, I mean, I think the world's your oyster, really. This idea of SILVR conditioning is so flexible. So within the original SILVR paper, they did all sorts of ideas like scribbling. So if they've got this person of like an image of a man, and they scribbled with like a paintbrush, being like, oh, here's some glasses, and then the model generated someone that had glasses on. So there's this like idea of being able to it's this flexibility. I don't know how to define and describe it, but like this sort of idea of maybe training a model that is aware of what's synthetically feasible as a post-processing step, and I can convert what's being generated, and like that is totally possible. It's just whether you can actually train that model, because the resources required for diffusion models are quite something.
Yeah, but I guess the previous question, sort of, you can put some bounds into that with some force fields, etc.
Yeah.
Okay, it's very interesting.
We'll take one question online. So does SILVR consider the 3D environment of the protein in the training/generation process?
No. So this is a very key point. Although all my figures I show the protein surface, SILVR during training is only trained on drug-like data. So it's trained on, well, the diffusion model is trained on drug-like data. So it's geome. And the model itself was only trained to generate molecules. The conditioning method that I have is only the fragments at the very last step. There's no consideration of the protein. I think in principle you could add information of the protein, and that's an idea I really want to explore. I think it'd be reasonably easy to add in some force field idea into silver with the protein, but that's not done. And actually, it's the last one here.
Yeah, that's the last question. Does silver work better with small sized or large sized reference fragments?
So silver, original silver, what I found was actually if you had more fragments, like 3 fragments and lots of atoms, the performance improves quite a lot. So having more atoms really helps. For silver 2, we had this quite interesting project that we're doing this sort of fragment linking in a large space. And so running these 2 fragments separately, the performance wasn't that great, but we actually added in a sort of a dummy guidance fragment in between. So we just enumerated some ideas of something that could exist in the space in between, just so that there's atoms to guide. And we're able to get a very large molecule being generated that maybe not on the order of PROTAC, but a really quite substantial fragment linking idea being achieved there. I don't think it's necessarily better on smaller, larger molecules. I think it's case specific as well, just by the nature of how things work.
Yeah, I think we'll take only one last question and then move on for the to respect the time. So please correct me, but are the bonds determined only at the last step by checking the interatomic distances and then with the valences? How stable are the results in practice?
Yeah, so the results are just atomic coordinates inferring the graph from the coordinates, and I was using OpenBabel for that. It was okay. There are so many weird issues. So like sometimes there are some hydrogen atoms that were missing because of how the generation process works, and then that carbon atom was seen as like a radical, and so I had a whole nightmare trying to be able to infer the graph. How stable are the results in practice? Not very. Silver, it's a novelty. I think it looks really nice as it exists. I don't think it's particularly useful yet, but silver 2, watch the space, silver 2 is really good. Yeah. Cool.
Okay, good. Yeah, thanks a lot, Nicholas, again. We bring talk. And we'll move to the last talk of the day. Okay. Share. One. Okay, and I just need to like this, like this. Better to use a pointer.
Just tap.
Slideshow, and I think we should be all set. So there's Donald and Richard talking about data mangling to data wrangling.
All right, thank you very much, ladies and gentlemen. I'm the startup act, and Richard will finish it. What I want to do, this is the first opportunity to really talk to people about what we've been designing for the last 3 years. And this is a lifting under the bonnet, right? This time you're going to see what goes on in it, not the results. Richard will show you how it works. I'm going to show you under the bonnet. Just a little bit about us, you know, I said 3 years ago, we formed after contemplating one of the simplest problems. We weren't looking for anything clever. We were looking for a way of dealing with data and data in lots of different formats. And we knew that in the drug industry and from discovery all the way through to the clinic, you get data presented in a mass of different formats, and you want to try and get it into a simple format, clean it up, and then spit it out and put it into some other workflow. So this talks about, you know, the simple things that we were trying to solve in all of this. But also we realized that things like stereochemistry were handled slightly differently between manufacturers, and we just thought of products, and we thought, well, let's try and look at that and see if we can get the cleanest product we can get, which deals with stereochemistry in a simple way and gets it right, has simple business rules. So we we set off and we thought, how do we build some software to do this? The problem is, if there's only a couple of you, it'll take you years and years. So we worked with a company called Conformations, who have about 700 staff. So we knew that any bit of expertise we'll be able to call on. And the idea is, and what I want from today is some feedback as to where we go from here, because there are lots of opportunities in AI, which we've just already heard. And I think the fact we can get a lot of big data aggregated, federated, then we've got to do something with it. We can clean it up. It's then the next step is to do something with it. And we've seen today already, you know, some things that we could use. Okay, so like all of these things, it's not just one product we've got. What it basically does is, in your organization, the Androit repository is dependent on lots of different parts of it. There's Amazon Web Services, so EPAM, as you'll all probably know, visualization tools like Capture, Mew, things like that are all produced by this company. We went to AG Grid because we wanted to have an interface that was like Excel, so that you could just get all your data together, manipulate it, and Richard will show you this later. But we wanted to be able to cut and paste it out. We just wanted it in a simplest form we could have. We also wanted it in a form that could be either internally housed within an organizational or sit on the cloud. We wanted it to be portable within different environments. So we built it on a Docker environment. Then we came to the fact that we needed a database. The underlying problem was, which database do we go to? What was the technology out there now, and where was the technology going? And we realized that we had disparate data. So we went from an elastic database with a view that we could, and we'll see a little bit later, we could exploit the fact that that was quite good at dealing with disparate data. So when we get files with different formats, different numbers of rows and columns, structures in them, no structures in them, we could deal with that side of it. Again, we again looked at, are we going to build our own predictive software? And we said, no, there's software out there. But we also wanted to build a platform where we weren't actually dependent on that, and that we could plug in any other predictive software via an API, and therefore deal with every organization's biases in software. Again, we went to a serverless environment, the reason being that we wanted to ensure that the product was constantly patched. And this was a long-term view for us as well, because not only were we going for a product that was going to be used in discovery environment, the long-term goal is to get this type of platform into the clinical environment as well. So we obviously realized that there had to be a lot of security issues that had to be addressed, that we always had to be on top of this, and holding that if we hold data in the cloud, it's got to be secure. And certainly for some customers, they're not as keen to have their data strewn across the cloud. So yeah, we built a system that could sit internally as well. We built a system that had APIs at various levels, simple APIs to quite complex ones, to allow people to plug in at different levels in the software. And again, I said we want it like Excel. We want it as simple as possible. Again, looking at what we wanted in terms of chemistry, we started off by saying we've got to get the chemistry right. We've got to be able to search quickly. We've got to be able to search both structure-based type searches and text and information-based searches. We wanted to work fast. We wanted it to work in an environment that, where people didn't need a lot of training to understand it, and we didn't have to support it in a great deal, because it just comes out the box and you can use it. Now, this really is under the bonnet. Now, if this doesn't make you all go to sleep, I don't know what will. But at the end of the day, we decided, how do we build a system that's resilient? It's written in Java, and we said, right, fine, let's look at the best implementation of Java where we're managing things like memory correctly. We'll be able to distribute it across systems, balancing. So basically, the real big message here is we went for an ACA type system where we've got an actors based system. So in this case, this is all the back end. And we talk to obviously Amazon Storage, and we talk to Elasticsearch, and we're talking to some other databases. We have a relational database, which we deliberately have there when the tasks we're dealing with are not applicable to NoSQL or Elasticsearch databases. And if anyone's had experience of that, there are some things where you can't do that in that environment. So that's the back end of it, and that really is under the bonnet. If we look at how the system functions, again, we wanted the most resilient system we could have. So when we built it on sharded Elasticsearch servers with a view that they would fire if one failed, we'd be safe. And this is a little bit out of date. We've actually had to expand it because of the amount of data we're housing within it, and this to get the indexing fast and to get the searching optimized. We went into an EC2 environment. So this was the back end I was just talking about, and the file systems that connect to that. But in this environment, this container environment, we said we've got to keep the software updated without disrupting users. So in this case, we inject. So we're using Jenkins to maintain a system so that it, for all intents and purposes, it's running and you don't know things are being modified as you're working. I don't want to spend too much time on this because a lot of you may know what Capture is, but one of the interests we had was to get something that would behave across platform, that would be sensible in the way it dealt with structures, primarily structures, but also reactions, because the obvious steps with this product is to take it on into the ELN type environment where reactions are important, and also where you're looking at metabolism and things like that, where you can search for metabolic pathways. We also wanted the ability to deal with chemical structures out of documents, and the reason for being able to convert a diagram in a document into a chemically usable structure was the fact that patents and things like that is really important. So in the functionality capture, we've got most of these things running. The other part of it is the reactions itself, and we are working on that at the moment. The other reason we were using Capture was actually the next step on for the, and you can see a little bit of this in Richard's demo, was the fact that we could view molecules in 3 dimensions. We could start to look at pulling in proteins and keep protein data within this, as well as small molecule data. And we've looked at all the differences between small molecules, PROTACs, ADCs, antibody data, all the way to genomic data. And the advantage of this is, whilst it started off as a tool for visualizing SD files, it's ended up with a more generic tool for storing data and searching. If I talk about its integration, I talked about Capture, I talked about the underlying database search cartridges, which are Bingo and QDP. We ended up we started with Bingo, and we've ended up moving on to QDP, which we've developed in conjunction with Quantori, and this allows us to do much faster searches across the sharded Elasticsearch databases. We've also got the ability to start building inline nodes, because we knew that this thing would be useful if it could link into a workflow. And also with developing the API, this ability to interact with other programs, maybe QM, things like that, was something in the back of our mind that we had to be able to integrate this. And again, part of our choice in why we went with Indigo was the fact that all of this structural matching, aromaticity, tautomers, business rules, and the way we represent things. Canonical smiles is always an interesting one, because I've had people say, oh, well, is that the best way of doing it, or there are other ways? Well, as far as we're concerned at the moment, this is the way to move forward. Again, we're using the fingerprints out of Indigo and RD kit for depending on what we're doing. Again, some of the features you'll see in the demo, so I won't go through all of this. But we're working now with R groups, we're working at enumeration, things like that, and therefore looking at the combinatorial chemistry market. We're looking at tying down business rules and the ability to fit in with the corporate structures, business rules. And finally, we've been working with EPAM and using Indigo for things like fingerprint collision avoidance and things like that. We're testing it to its limits, try and understand where its limits really are. At the moment, we're comfortable with it. Also, the bit that we can see that we've tied a lot of things together, and a lot of things are dependent on QDP, which is what we built with Quantori. And this allows us to, when we're doing searches across elastic searches, they are quite difficult in some respects, because it's not like SQL databases. They behave slightly differently. So we had to optimize that. And when we first started it, these were appallingly slow. I'll admit that. But with a lot of work and understanding, we've started to get this. And I'm hoping to, in a minute, Richard will get up and show you how quickly these things occur. But we are in a position now to say that we've got a layer that we've built over the last 2 years, which allows us to search very rapidly. And there is actually an add-on to this to do the searches through a GPU type environment. So we're looking at even faster searches, and I can guarantee in the next version of that will be an option to do very rapid structural searches. So I'm coming to the end of it to basically say, look, we went to build a simple product that's easy to use, that has easy interfaces, that is easily deployed, that has reasonable search chemistry, which is expanding as we speak, the ability to search across different data types, and the ability to work fast, but most importantly, and we'll see this in a minute, a modern interface, one that's really simple and clean, and you can use it. And for the simple tasks, you'll see it's amazing. Okay. Well, now
Thanks, Don.
Just make sure that we're sharing.
You've done it.
Okay, so
You've
you have
done a great
Firefox
job.
and Safari, so yes.
Okay.
Just play on with that.
You've done a great job of making it look very complicated, and now I'm going to try and make it look very simple. So this is the interface, and you'll see when you first get username and password, you'll sign in, and you'll just see a blank canvas. Now, bear in mind, I'm doing a live demo on someone else's computer. So that's a fingers crossed moment. So you'll see it, and you'll have some data. So I'm going to have the example of you're working on a compound series, and so you've got a base set of molecules, and you've sent them off, and you've got some additional data. So I'm using a really small data set at the moment. You can see it's uploading, initializing, indexing everything. So I'm going to use a multi-million data set next, but to show you the principle of it, I'm going to use a tiny data set. So one of the problems that we've solved that we're really pleased about is the stereochemistry, so the chirality. So this is alanine, That's the S, the R, and no chiral data. And this is quinine, which has a lot of stereocenters. So if you then get some additional data, which you want to combine with this, now imagine, I'm just showing a small data set, so you can see what happens. But if you do it over thousands, you won't be able to see it very easily for the purpose of a demo. But you've got extra information on all these different molecules. So then what you can do, you can just tack it together. So if you just do a combination, just combine the two together. It makes it really easy to look at the data and bring the two entities together. Now, bear in mind all the complicated stuff that Don has seen. And every time I show this to somebody, they said, can you make it more Excel-like? So we did, in fact. So there's all sorts of neat stuff. So you can move columns around. You can lock columns like that. So when you're scrolling across, this stays in one place. You can cut and paste. You can export into Excel, all that kind of stuff, which is pretty cool. But one of the really cool things is, whilst you're doing that, you can say, okay, I've got the additional data. Let's remove all those duplicates. Okay. So you can remove those duplicates. And it will give you a file. You've seen you add 4 and 10, you get 16. So each row is a different molecule. And there you go, I've got 6, because within that data, so it's figured out that the R and the S alanine are different. The one without any chiral information is different. It's tacked the information across. So let me scroll across here. Oh, there's only that much data. It's added extra columns, so smarts and then smarts 2, where the data didn't exist. It's also noticed that this quinine comes with a salt. This quinine has carbon-14 in it, which makes it different to this quinine, which is just plain old quinine, which is pretty cool. And you can do stuff, I know Don mentioned that you can add things in. So you can add in a user-defined column, text or numeric, and you can calculate different structures, for example, different properties. For example, at random, a ring count. But there's all sorts of things you can add in there. And one didn't work properly because it could have solved it. Then if you go to the larger, which one's this, Safari? So here's the real, I prepared this one earlier because it will ingest. So this is a demo version and it will ingest about 5,000 molecules a minute. But in this, there's just under we've got a notional limit of 10 million. So this is a demo version. We can go up to many, many more than that. But we just thought we'd just do this for a demo version and we hand out the keys to this so people can have a look. So here's one I prepared earlier. So what we're going to do is a substructure search. Oops. Not for 2. Like I said, it's not my computer, and that's stuck. Huh. Oh, no, that's not working. 1 second. It's been sat open for a long time with a desk, so it might have just logged me out. Right. There we go. Okay, so there's a cyclopentadiene, and across these 10 millimolecules, just under, we can do a substructure search, an exact search, a similarity search. Let's do a substructure search across all of the 18 files in total, some of which have got quite a lot of molecules in, and we'll see how quickly that's going to come back containing all the molecules with a cyclopentadiene substructure. There we go. That one took a bit longer. And there we go. We have our 873 hits back very quickly. This is a relatively small version of the system. So imagine if you've seen these are molecules. So you're now trying to find a molecule you want to buy from, and as you were saying, you want to go out, search what's available, find out what it's going to cost and bring it together. So you found all these and it's okay, let's have the hits that we found from our 10 millimolecules and we'll pull those together into one convenient file. So hopefully what I'm showing you here is how quickly you can get millions of molecules, throw them around, manipulate them, export them. I didn't open the Excel file actually, did I? Where's the downloads up? Not, oops. Don't open your email, sorry about that. That's good. So I pulled together that list of hits, 873, and oh dear, as you can see, not unsurprisingly, there's a whole bunch of duplicates in there. So you can say, okay, that's nice. Why don't we take that whole load of hits and deduplicate it and do a true merge? So what I'm going to do is take the refined hits from that, go through with the fingerprints, recognize each different molecule, And then when it finds one that's the same, it's going to tack the extra data on to the end, so put another column on and provide you with a short list of all the different molecules that are available to buy. And there you go. There's the 270 hits. And as you can see, it's added in. It says, trying to find where it's done it. It is added in where there's extra data that's not contained. It adds in a different column, so it doesn't delete anything away. And there are all sorts of ways you can then go in and filter further. So if you want to go in and look for various different things, you can go and do a Boolean search for all sorts of stuff until eventually you get down to the molecule you want. Now I can go and show you all sorts of other stuff. I think we're just about there for the end of the live demo. And it's pretty cool. You can open all sorts of different windows. But it's a demo, not a training session, and you can always come to me and ask me, and I'll give you one individually. That's it for the demo. Any questions? Oh, we've not got the Zoom up properly here, have we? So will it come through? He says, as in the Zoom chat.
Yeah, just if you go. Yeah.
Okay.
You can also check the participants to see if there's anyone with a raised hand. It doesn't seem to be.
Doesn't seem to be it.
Yeah.
The demo was so good.
Well, smoothly. Yeah.
It worked. Yeah.
Yeah.
Okay. All right. Thanks, everyone. I'll hand back to Benoit.
Yeah. Thank you very much.
Okay.
Okay, so I think if we don't have any further question, yeah, maybe there's Chris asking. Oh yeah, thanks.
Any plans to put anything like plotting
Yes,
features on it?
Yeah.
The answer to that is yes, because AG Grid itself is a product that was used in the city, and that was part of the reason why we went that route. Was that it was Excel like, but it also contains which we haven't activated yet because we need to check how it deals with the index, the underlying database. But yes, that will come in the next version or one of the sub versions. But yes, it'll be simple plotting. But the idea then is to tie in R with some code, because what we'd like to do is the ability to transpose tables, things like that. Or these are things where you've got your data and it's too many columns or too many rows and I need it transposed. So that's the idea. So yes, those things will be coming in the next couple of sub versions.
Okay, well, thank you again for your brilliant talk and demonstration.
Thank you.